Welcome to our 16th lecture here in Chemistry 51C. You may find yourself doing some improvement or repair or do-it-yourself project that involves a requirement for lithium grease, white lithium grease. Why would you end up using something like white lithium grease, and what is that stuff? Generally use that in applications where you're expecting high temperature or low temperature. At high temperature, it doesn't melt and become all runny and snotty and come off of the parts that you're trying to keep lubricated. Or if you happen to go to very low temperatures, maybe in the Arctic, it wouldn't get all solid and cakey and then flake off. And so those are applications where you want to use white lithium grease. And it got me interested in what is white lithium grease? It seems odd to me that a lubricant should be white. It turns out that lithium grease is closely connected to castor oil. And from my youth, castor oil, it was maybe a kind of meme from the last century where for kids who ate too much food or ate unhealthy food and got a stomachache, they were forced to take castor oil, maybe as a punishment or as a medicine or as both. I'm not really sure. Let's go ahead and take a look at that.
I'm tired of this. Oh. Now, come on. Open your mouth. You hear me? Open your mouth. Now, look. Open it wide. Like this. Ah.
I don't want it.
Boy, what could be less interesting than castor oil? Turns out that castor oil is really interesting. Let's go ahead and talk about this lithium grease situation here and what's that about. It turns out that you generate lithium grease. Wow. Let me try to bring back my slide. You make lithium grease from castor oil, which is pressed from castor beans. So over here on the right side of your screen is the chemical structure of castor oil. And it looks like a fat, a little bit like a lipid from the molecules that you find in the outside of cells, but it's really a fat molecule. But unlike the fat molecules that you find in your body, all three chains on this triester, that's what a fat is, it's a triester of glycerol. All three of the chains are identical. Whereas if I take a fat molecule out of your body, it turns out that you're not going to be able to see the same chain. What you'll see is some of the chains have one cis double bond, another chain might have two cis double bonds, another one might have four cis double bonds. Very rarely would they ever have a hydroxy group on there. So it's kind of extraordinary to find a fat molecule from nature where all three chains are identical. And that's castor oil. And what they do is they take industrially castor oil and they hydrogenate the double bond with hydrogen and an industrial catalyst like you've learned with palladium and carbon. And then they hydrolyze, they cleave these esters using base-promoted hydrolysis, but they don't use sodium hydroxide. They use lithium hydroxide. So what you get are soap molecules. But unlike soap molecules in the white bar of ivory soap you use to wash your hands, instead of sodium carboxylates, they're lithium carboxylates. And it's this hydroxy steric acid, the lithium salt, that you buy as white lithium grease. It's actually lithium soap. Really interesting that substituting sodium for lithium makes this much more greasy and less soapy. All right, let's go ahead and go to the topic for today's lecture, which we finished all of this chemistry from our last chapter on carboxylic acid derivatives, on esters, on base-promoted hydrolysis, and let's move on to some really important stuff for the field of organic chemistry, which is forming carbanions, alpha to carbonyl groups. Okay, so we just finished a chapter on carboxylic acid derivatives, and now we're talking about these protons, alpha to carbonyls. So really this chapter is mainly focused on carbanions. The chemistry of this chapter is enols, which are neutral, and enolates. It's the enolates that really do all the work in this chapter and the next chapter. And you've seen carbanions before. Let me just remind you of where you've seen something akin to free carbanions. I'm not talking about alkyl lithiums or alkyl magnesium halides. I'm talking about something more like a free carbanion. And you learned back in the chapter on alkynes that you could take alkynes and use a strong base, sodium amide is the base that you used, and you could deprotonate alpha on that carbon atom that's at the end of the alkyl chain. And that generates a carbanion that then you could then use for SN2 reactions. Now, SN2 reactions are not very good, but this is kind of all you had for 6 months. They way overused this reaction, but it was really the only carbanion that you had at your disposal. And what we're doing in this chapter is we're learning about a new class of carbanions, a powerful class of carbanions, a class of carbanions that's used in nature, a class of carbanions that's used in organic synthesis, unlike these acetylide anions, which are sometimes used, but not as commonly. And so what we're going to show you and focus on over and over again is when you have protons at this carbon atom that is right next to a carbonyl, we refer to this as the alpha position, you can deprotonate at that position. You can remove those protons if you use a base that's strong enough. And we'll talk more about what kinds of bases you need to use. So when you do that reaction, you're going to generate a carbanion. Let me go ahead and draw the structure of that carbanion, and then we can talk about how resonance makes it possible to deprotonate selectively at that position and not at other positions in the molecule. So here's one possible resonance structure of the carbanion. There's another mechanism we can draw for this deprotonation, which really uses the carbonyl. It helps us to understand why the carbonyl makes that position so acidic. So we can also draw that same reaction with just as much correctness by attacking the proton and giving the electrons to the carbonyl. You can either attack the carbonyl, or you can draw your arrow ending in the middle of the bond. Just be precise about that. And then we'll push the electrons up to the oxygen. And that's why this proton is so easy to deprotonate, is because we can push the negative charge up onto an electronegative oxygen atom. Let's go ahead and draw that resonance structure that we get when we show the arrow push the electrons all the way up to that oxygen. The resonance structure that we generate looks like this. And these are simply resonance structures of each other. I can go back and forth by drawing resonance arrows. Right? There's no difference between these two. Anything that I can do with this one, like using it for SN2 reactions, I could also do with this bottom structure. So in this chapter, what we're going to see a lot of is that we're going to be making these special carbanions right next to carbonyls. We call these enolates because they look kind of like an alkene with an alcoholate on there with a negative charge. That's what that 8 means. There's a negative charge on the oxygen. So this is an enol-8. 8 means something with a minus charge. Now I'm going to show you an SN2 reaction using this top resonance structure, but you could do just as easily the arrow pushing by using the bottom resonance structure. Let's go ahead and watch how that works. Let's suppose we have this and we have some sort of alkyl halide. Let me take in as an example methyl iodide. I love that. It's got no beta protons, so we don't have to worry about elimination reactions, there's no competing E2 elimination. And so what a great way to form carbon-carbon bonds. Make carbanions next to carbonyls, these special species called enolates, and then use those for CC bond formation. And we're going to do this over and over in this chapter. We could do exactly the same arrow pushing using the bottom structure, which is more correct. Neither is more correct. I like the top one. The book really, I think, tends to favor this bottom resonance depiction, but we can do the same reaction. We can depict the same process just as correctly by using this enolate resonance structure. I can take my same electrophile, methyl iodide, and I can start my arrow pushing here from the oxygen lone pair, and then push over like this, and then push out the leading group. And that leads, I don't even need to, it leads to the same structure. These mean exactly the same thing, these two different ways of pushing arrows. I tend to favor the top when you're just starting to learn about enolates, because I feel like it's more obvious why this carbon is so nucleophilic. I think the book tends to favor a more traditional depiction of enolates, which kind of belies the fact that that carbon right there, next to what used to be the carbonyl, is really a nucleophilic carbon. Now, if you're interested in making bonds to carbon or attacking carbon electrophiles, you you'll end up using this carbon, not the oxygen atom. And that's what you have to get used to in this chapter. So let's go ahead and talk about that over and over and over again. Get used to that arrow pushing. Now, this chapter talks about enolates, which have a negative charge, and enols, which are the neutral form. And you've heard about enols before. Way back in the chapter on alkynes, we learned about two different reactions that generate enols. One is this mercury catalyzed addition of water across a CC triple bond, and that occurs regiochemically to favor putting the hydroxy on the more substituted carbon of an unsymmetrical alkyne. You also learned about a two-step hydroboration oxidation sequence, which gives you the opposite regiochemistry, but still gives you an enol. And they told you in that chapter, they told you, well, you don't actually isolate the enol, it isomerizes to this constitutional isomer called a tautomer, that's got a keto form to it. And they didn't tell you the mechanism. It's like they made you wait until, what are we, like half a year later to learn what's going on in this reaction. So we're going to talk about this isomerization process. It's not resonance, because there's atoms moving from one place to another. That's not resonance. So we're going to go ahead and talk about this very special type of isomerization between two very special types of constitutional isomers. They share the same molecular formula. That's about all you can say. They're not stereoisomers, they're not resonance structures, they're not enantiomers, and we have a special word for these, tautomer. Tautomer means you've simply picked up a proton from one part of a molecule and you've moved that proton to another part of the molecule. That's what tautomer means. So remember, do not draw a resonance structure. This is an equilibrium characterizable by an equilibrium constant. And I'll just tell you right now, in most cases, in virtually all cases, the keto tautomer is favored. In organic chemistry, so much of organic chemistry is driven by the fact that carbon-oxygen double bonds are more stable than carbon-carbon double bonds. CO double bonds, carbonyls, are more stable. That's like carbon dioxide. When you burn things, they generate carbon dioxide. That's the thermodynamic sink for most for burning stuff. So very heavily favored, the keto tautomer. But there's a couple of exceptions. Let me see if I can give you two exceptions where, and these are rare exceptions, where keto tautomers are not favored. So one place where the enol tautomer is favored is with phenol. So phenol is actually an enol. And you could draw that in a keto tautomer form where I put the H down over here. But if you do that, the keto form is not aromatic. So this is, in the case of phenol, this is the enol form. Let me go ahead and circle the enol part of that molecule. This is the favored form of phenol. It's not the one where you put a carbonyl group there, because you lose aromaticity. Aromaticity is worth 36 kilocalories per mole. So there's a huge driving force to have the double bond as part of that ring. I hope that's kind of obvious, that you don't draw phenol in the keto form, because it really wants to be aromatic. Let me show you another case where the keto form doesn't heavily dominate. This is kind of a special situation. And that's in the case of 1,3-dicarbonyl compounds. Let me draw first the tautomer of a 1,3-dicarbonyl that's favored, and then we'll talk about the equilibrium form, which would be the keto form. And both sides could form the enol. This is a symmetrical molecule, so the two carbonyl groups are not distinguishable. So what's happening here? Well, there used to be two H's here, and now there's only one H. You can see the H is moving positions. That's not resonance. That's isomerization. If there's atoms moving, it cannot be a resonance structure. And in this particular case, the ratio of these two species at equilibrium, meaning if you put this in an NMR tube, you'd see two compounds in your NMR. You can't stop it from equilibrating. You can't just set the molecule in your flask and say, don't move. There's going to be 6.02 times 10 to the 23rd molecules in your flask, and they will be present in a 3-to-1 ratio in your flask. You can't stop this equilibration from occurring. That you'll instantly establish equal or almost instantly establish equilibrium. So why is the enol tautomer so stable? This is a special case. Like for acetone, you have almost no, you have very little enol present in a bottle of acetone. Well, the reason that the enol tautomer is so favored is first that there's resonance stabilization. We have resonance here where this lone pair is donating. I'm not going to draw all the arrows, but the lone pairs are donating into the carbonyl if I draw enough arrows. So I'll just write the word resonance there. That's one reason why this form is favored. The other reason why this is favored is there's a stabilizing hydrogen bond in this species, in this enol form of this 1,3-dicarbonyl. So I'll just write the word H bond here. So this is kind of a special case, but generally you take a typical ketone, cyclohexanone, acetone, methyl, ethyl ketone, esters, amides. It's really almost, it's over 99.99% of the keto tautomer. It's only these two cases where you'll see substantial amounts of enol tautomers. And even in the case of this 1,3-dicarbonyl, it's not 100% enol. You still have plenty of the 1,3-dicarbonyl form. Back and forth, they're isomerizing back and forth. We need to talk about what is the mechanism for this isomerization? It's not just resonance. There's atoms moving around, and it's not a one-step mechanism. And maybe that's why they didn't want to tell you about this back when we covered enols in the alkyne chapter. Maybe they thought your brain would explode or something. So they didn't want to let you in on this secret about what's happening here for keto, what we call keto-enol tautomerization, this two-step isomerization process. Okay, so there are actually two hypothetical mechanisms for catalyzing tautomerization from the keto to the enol form and the enol form to the keto form. And they're not equally important. In fact, the base catalyzed mechanism for this isomerization reaction is not at all important. So I'll talk about that in a second. So let's talk about the acid-catalyzed mechanism. So when you have a carbonyl compound, it can tautomerize to the enol form. Now, when you're just starting out, you might have the tendency to say, oh, gee, well, I see what happened there. You started with a CC single bond, and now you have a CC double bond. You're completely missing the point of what happened if that's what you're focusing on. You should not be focusing on the fact that there's a new CC double bond here in this tautomer. You should be focusing on the fact that there's no longer a hydrogen on that carbon atom. And this is the biggest problem that I see with people who don't make a transition from Chem 51A to Chem 51B to Chem 51C, is they don't see the hydrogens. You started off with 3 hydrogens over here, and then over here, plain as day, there's only 2. So if I ask you what happened here, I hope you say you lost a hydrogen. In fact, you can see where it appeared. It appeared on the oxygen. Don't just say there's a CC double bond, because you're never going to be able to figure out what's going on. Let's take a look at the mechanism under acidic conditions. If I put an acid in there, and it doesn't take a strong acid, this is such a facile process. You could just put pure acetone in solution, and the other acetone molecules, the oxygen molecules on the glass SiO2, silicon dioxide is kind of the generic chemical structure for glass. Anything with a lone pair can catalyze this reaction, or a surface that has H's, available H's. The mechanism starts off with protonation of the carbonyl. You already know you can protonate carbonyl. That's the mechanism for the reaction. You don't have to generate a high equilibrium amount of this tautomer in solution. Let's go ahead and draw out of this protonated carbonyl in solution. Let's go ahead and draw out that protonated carbonyl. And here's our protonated carbonyl. It's an oxonium ion. We have the conjugate base left over from our acid. We draw the lone pairs on that conjugate base, and now we deprotonate. Now it's absolutely true that under these conditions you could pull the proton off of the oxonium ion. We'll talk about that in a second. But what I'm going to do is I'm going to draw the arrow pushing that takes us over here to the product. So I can make, when I move the electrons from this H carbon bond, I can either leave it here in the middle of the CC double bond, or I can attack the carbonyl. Just be precise about how you draw that. Most of the time I like to attack the carbonyl carbon with my curved arrow. It just feels more natural. I didn't do that on the last slide. But that gives you the enol tautomer. These are tautomers. They have an isomeric relationship. They share the same molecular formula. That's about their constitutional isomers. And a special type of constitutional isomer where they just differ in the position of a proton. So that's tautomerization. Now let's go ahead and draw the mechanism going backwards. I don't want to add more arrows to this top mechanism because if you have two sets of arrows, then it's not a correct arrow pushing mechanism. So let me separately draw the backwards mechanism. Everything's in equilibrium here. So if I have an enol tautomer and I want to draw a mechanism for tautomerization, I'm going to want to add another proton. We only have 2 protons, so I want to add a third proton to that carbon. And here's how I would draw that arrow pushing. I would start with the oxygen atom, and I would push the electrons here. That resonance donation into this CC double bond is why this alkene is so reactive on this end carbon. That's why it's so reactive and so basic and so nucleophilic on that carbon. I'm going to use the pi electrons to grab the proton, and you might think, well, shouldn't my arrow start with this carbon atom on the end? No. Arrows start with electrons, not with atoms. I realize that the proton ends up on this atom, but our rule is that our curved arrows have to start with a pair of electrons. That means the bond. So it might be frustrating to you that you're not allowed to start your arrow from this end atom, even though that's where the proton ends up. That's the rules of arrow pushing. And arrow pushing is powerful if you obey the rules. Okay, let's go ahead and draw the next. It has to be the same intermediates I just drew if you're going forwards and backwards in an equilibrium process. There's a principle called microscopic reversibility that says you have to go through the same intermediates going forward and backward in a mechanism if everything's in equilibrium. There's not like some secret intermediates that it goes through that the other mechanism didn't know about. So here's what we get according to our arrow pushing. Of course, it has to be the same stuff, but we have different arrows if we're going in the backwards direction. So now I don't want to pull the proton off of here. That just takes me back. That's boring. We already did that up above. I want to deprotonate. Oh, sorry. We don't want to take the proton off the carbon atom because that's boring. It takes us back. We want to take the proton off of this oxonium ion in order to regenerate our keto group. And that's what leads to, so this is the mechanism for keto-enol tautomerization going forward. And then I drew the same intermediates and drew the arrow pushing for the mechanism going backwards. So again, there's a base promoted mechanism where you deprotonate here to make a carbanion, an enolate. But the enol is not important under those conditions. If you're making enolates, the enolates are doing all the work. The enols are, if there's any in there, are just sitting there doing nothing during the mechanism. So it's not really important to show you the base catalyzed mechanism. That's not to say it's not important to think about bases deprotonating carbonyl compounds next to the carbonyl. That's super important. That's what this chapter is about. Let's go ahead and talk about that. Let's talk about bases. What do bases do? We have carbonyl compounds. And those carbonyl compounds have hydrogens at that special position. Now we have a naming system that's the same naming system they use in biology, or maybe that the biologists borrowed for naming amino acids. The positions on a carbonyl compound, we use Greek lettering to indicate how far away they are from the carbonyl group. So the carbon that's directly attached to the carbonyl group, we call that the alpha carbon. And the carbon that's 2 atoms away from the carbonyl group, we call that the beta carbon. Guess what? The carbon atom that's 3 atoms away is called the gamma carbon. And it'll be delta, epsilon. Those positions are not usually important. And we might have introduced this before talking about alpha, beta, unsaturated carbonyls, or we might have talked about beta elimination. So we've used this kind of Greek lettering before to indicate relative positioning. So here we're talking about relative to the carbonyl. But when we're talking carbonyl chemistry and enolates, it's the alpha position right next door to that carbonyl. Not the carbonyl carbon itself. You can't deprotonate that if it's an aldehyde. It's one carbon over from the carbonyl. So let's go ahead and think about what happens when we treat compounds like this with base. Because what we're going to find is that bases can deprotonate alpha. They can't pull protons off the beta position or the gamma position or the delta position, or the epsilon position, or any other position in this chain, only the alpha position. Why? And what kinds of bases would you need to pull those protons off of that position? So if I give you a ketone here, In this case, I'm giving you one with a quaternary center. If I drew the structure of T-butyl, you'd see there's no hydrogens on the other side. So there's really only one. That's why I'm picking this particular ketone. Is only the carbons only the carbon on the right has hydrogens on it. So this alpha carbon here has protons on there, and let's go ahead and take a look at what we expect to be happening when we treat this with a base of some kind. Well, that depends on the base. The problem is that so far you've been exposed to a very limited selection of bases, and probably when I say the word strong base, what would probably spring to your mind, unfortunately, is potassium T-butoxide. That's probably the strongest base that you've been exposed to when we use the word base. It's not as basic as an alkylithium or a Grignard reagent, but when we use an alkylithium or a Grignard reagent, we're not generally trying to use it as a base. We're trying to use it as a nucleophile. Tertiary, like T-butoxide or alkoxides, we're usually using those as bases, right? Only like months ago, they told you about SN2. That's not really common to make carbon-oxygen bonds with alkoxides. In fact, that's pretty rare. Okay, so let's take maybe one of the strongest bases you're familiar with, potassium T-butoxide, and imagine what would happen if we tried to pull a proton from next to this carbonyl, from the alpha position next to the carbonyl. These protons are way more acidic than just a simple alkane. They have a pK of about 20. So not as acidic as an OH, like 10,000 times less acidic than an OH. When you do this reaction, I don't want to focus on the arrow pushing just right now. I want to focus on the equilibrium. You deprotonate this carbon, the alpha carbon, and then the carbanion would pull the proton back off, and then you would deprotonate. You'd go back and forth, and it would generate an equilibrium. But the equilibrium very heavily lies on this side, right? The carbon atom wants those protons more than the T-butoxide does. And so you'll generate at equilibrium a small amount. Maybe I should write T-butoxide, T-butyl group there. So you'll generate a small amount of this enolate at equilibrium. And then over here on this side of the equation, we would have an alcohol, which has a pK. It's actually harder to deprotonate the T-butanol a little bit than just plain water. I'll go ahead and give you the pK for that proton there. It's about 18, so about 100 times harder to pull that proton. The bottom line is that even in our most optimistic scenario here, right, if there's an acid on this side of the equation and there's an acid on that side of the equation, and I know that they're 2 pKa units different, that tells me the ratio of these species is going to be 100 to 1, 10 to the 2 to 1. There's one of these acids is 100 times more powerful. That's what the log scale pK tells me. And this acid is more acidic and this is less acidic. The equilibrium is going to lie in this direction. The ratio of these at equilibrium is going to be about 100 for this anion to 1. 100 parts of these things to 1 of these. So for every 100 molecules of ketone that I go look at in solution, only 1 out of 100 will be deprotonated. Very little of your ketone will exist as this enolate if you use a lame base like T-butoxide. Let me show you the base you should use if you want to deprotonate next to a carbonyl. It's this new base that you haven't seen before. It's called lithium diisopropylamide. And we'll talk more about that in a second. Let me show you what happens when you use a good base, like lithium diisopropylamide. The pK of these protons is not any different. It's the same molecule. It still has a pK of 20. But let's look at the conjugate acid here that you generate once diisopropylamide anion pulls off a proton. So now let me use my black pen here. My enolate is going to have this same structure. That won't be any different. But the equilibrium will now very heavily lie on this side. And the pKa for this proton, amine NHs are not at all acidic. The pKa of that NH proton on a simple amine dimethylamine, ammonia, those types of species, somewhere on the order of about 35. Depends on exactly, that depends on the structure of what's attached to that amino group. But if you look at the difference here, it's not just 2 log orders difference, it's 15 log orders different, 10 to the 15. Like if I put 1 and 15 zeros, you're starting to get a sense for the equilibrium ratios here. I can't draw an arrow that's 10 to the 15 times smaller unless I drew it like literally the size of the atom. But this, the equilibrium lies to this side. I'm not going to draw the numerical ratio, but the yield for this process would be 99.999. I have to go and draw 15 of these 9s. I'm not going to draw all of them out, right? If you want to generate a high yield of the enolate, don't use t-butoxide. You only get a 1% yield of the enolate, and it'll still be in equilibrium. If you want to generate enolate, completely convert your carbonyl compound to an enolate instantaneously. In quantitative yield, you use LDA. Don't use t-butoxide. That's only for people who can't remember any new reagents since the first quarter of our organic chemistry sequence. But we've got there's a new base in town, and that base is LDA. Let's go ahead and take a look at how the detailed structure of the carbonyl affects the acidity. It turns out that what's on the other side of that carbonyl has a pretty serious effect on the acidity of the CH. And in particular, if I have heteroatoms that have lone pairs that can donate through resonance into the carbonyl, it's going to make it harder to pull this proton off. And the only reason we can pull this proton off over here is because the electrons go into the carbonyl group. But if I've already got a lone pair donating into that carbonyl group, it's a lot harder to pull this proton off because, right, there's already something donating in through resonance. There's already a lone pair donating in through resonance. So how are you going to get these electrons to donate into the carbonyl? So if you put an oxygen with a lone pair next to this carbonyl, it's harder to deprotonate. If you put a nitrogen, wow, nitrogen lone pairs are really nucleophilic. A nitrogen lone pair really makes it dramatically less acidic. Let's go ahead and take a look at how those effects play out. You know, when I think of the pKa of a carbonyl compound, if you just ask me, what's the pKa of a carbonyl compound? I usually think of acetone and I write 20. That's kind of the number that sticks in my head. What's the pKa for both? Acetone is kind of the canonical ketone or carbonyl compound that has CHs next door. That's all that's next door is CHs in acetone. Now, aldehydes are more acidic. Aldehydes are more electrophilic. Aldehydes are just more reactive. That carbonyl group of an aldehyde is like a secondary carbocation versus a tertiary carbocation. And it turns out that the pKa of this is pretty serious. You know, it's about 1,000 times more acidic. Aldehydes can be kind of tough to work with. Sometimes just a little bit of base and you're starting to generate enolates that go attacking things. And it's just, you get tar out of the reaction because a lot of bad stuff starts happening once you start generating enolates without control. Ketones just a lot more tame, a lot easier to work with without unwanted deprotonation. So this aldehydes can be tricky, especially acid aldehyde is a really pain in the rear molecule to work with in the lab. It's volatile is one of the issues. It's so electrophilic. Okay, when you have a lone pair next door, wow, that lone pair there, really just makes it, since it's donating, that lone pair is donating into the carbonyl. Sorry, I've blurred the lone pair. It's donating into the carbonyl. It's harder to deprotonate. How much harder? 100,000 times harder. 10 to the 5th harder to pull the protons off. The pK is five orders of magnitude higher. I almost hated the fact that more acidic means higher pK. You know, at this stage for you, you're probably like me. It's kind of this opposite thing that you have to. So more acidic means higher pK. Sorry, more acidic means lower pK. God, I'm just trying to keep the more acidic means lower pK, and that doesn't make sense. So now when we go to a really nucleophilic lone pair, let me just make them really big. Wow, that's so strongly donating. So now it's really hard to pick up a proton and push the electrons to the carbonyl because there's this really strongly donating lone pair of nitrogen next door. And so now it's 10 orders of magnitude less acidic than just a regular ketone. 10 to the 10 less acidic, 10 billion times less acidic because of that nitrogen lone pair next door, that stupid, annoying, but again, if you put LDA in, no problem pulling that proton off. LDA is just so screaming aggressive. LDA doesn't care whether it's an aldehyde, ketone, ester, amide. LDA just yanks the proton off, not a care in the world about that. Now, LDA was developed, I think it was around the early 1970s when it was introduced. And before that, we didn't have super strong bases to deprotonate next to carbonyl groups, or at least well-controlled ones. And before that, we used to restrict our carbanion enolate chemistry to ones that were super easy to deprotonate. And it turns out that if you have two carbonyls next, attached to the same carbon, those CHs in between them are really acidic when their two carbonyls are directly attached. So when you have two ketones directly attached to an alpha carbon instead of one, now that's so acidic. My gosh, you know, water has a pK of 16. This is 10 to the 7th more acidic than water. It's 10 to the 7th more. Those CH protons in between are 10 million times more acidic than water. Two esters, it's not quite as, but it's still more acidic than water. Water has a pK around 16. You know, that's like 1,000 times more acidic than water. That has a pretty serious implications for how you work with these and what lengths you have to go through to stick a proton on there when you're trying to work up a reaction that occurred under basic conditions. So two carbonyls really acidify those CHs when they're both attached to the same carbon. Okay, this is an important effect. I expect you to remember the order of this effect. I mean, these are not subtle things. When you're talking about 10 to the 10th, I expect you to know effects that are on the order of 10 to the 5th, 100,000 times, 10 million times. Those are an important effect in organic chemistry and relate to your understanding of resonance. Okay, enolates. Boy, that's this chapter. So super important here for the, let's go ahead and get kind of a broad overview of how do enolates fit into the grand scheme of things, because we're going to keep seeing enolates coming up. So we're going to go through a lot of work. Here in the laboratory, you go through a lot of work to make enolates and then try to control them so they do what you want. Let me show you what you don't want to do. One of the things that we said is if you make an alkylithium reagent, you keep those away from water. If you're going through the trouble of making an alkylithium reagent or buying an alkylithium reagent or making a Grignard reagent, you do not let them touch water. You do not let them touch wet air like you're breathing right now. We run all our reactions under anhydrous, oxygen-free nitrogen, purified nitrogen gas, because nitrogen gas doesn't react with anything. So when we go through the trouble of making enolates under basic additions, we're usually going to try to avoid water. Right? If we're going through the trouble of making this carbon atom over here, nucleophilic, the last thing in the world that we want to happen is we don't want to just stick a proton back on there, because we always made this by pulling a proton off. Why would we want to stick a proton back on something? So if we just finish pulling the proton off, so really we have to try to avoid this type of, we'll try to choose conditions to try to avoid protonation of our enolates. It happens sometimes as a side reaction. Sometimes it happens as an unwanted part of an equilibrium process, like trying to use T-butoxide. But we're generally not trying to do this on purpose. That's pretty boring. What are we doing with enolates in this chapter? Here's the stuff we're doing with enolates. So in chapter 23 of the Janus Gorzynski-Smith organic chemistry textbook, we're using enolates in chapter 23 to do SN2 reactions. Boring, but still has some importance, but not the main principal reason why we're generating enolates. So we'll show you that just like you could do SN2 reactions and displace leaving groups like bromides or iodides or tosylates, we can do those same kinds of SN2 displacement reactions. And that's what the focus of this chapter is about. We're going to be making enolates, and then you're going to be getting that carbon atom at the end there to form new carbon-carbon bonds. That's really, so let's, I can't resist drawing that out just because it's so amazing. There we go. We form that new carbon-carbon bond. That's a big thing. That's our chapter here. So remember that. I'll keep telling you. And what's coming up in chapter 24? More enolate chemistry. That's what's coming up in chapter 24. And you know what we're going to use enolates to do in chapter 24? Something very cool that's related to biology, that's related to modern organic synthesis, and that's using enolates to attack carbonyls. That's what we do with good nucleophiles in the field of organic chemistry and in biology, is when you've got a good nucleophile, you attack carbonyls with those good nucleophiles. So the pattern we're going to see in chapter 24 over and over and over again is using enolates to attack carbonyl groups to make carbon-carbon bonds. We'll also see some stabilized enolates attacking where we've got 1,3-dicarbonyl. So if you deprotonate between two carbonyl groups, you'll end up with, this is one possible resonance structure. So we'll also see in chapter 24 where we've pulled a proton from between two carbonyls, and then that enolate then attacks, oh, I forgot to carbonyl. I forgot to draw my carbonyl. Then attacks a carbonyl compound. That's what's, so it's, you have to learn about enolates. You have to embrace this concept of deprotonating next to carbonyls and then using them as nucleophiles. That's really the theme of this chapter. So we've got a new base. We've got a new base to make this that's worthy of our chemistry. And that's lithium diisopropylamide. Let's take a closer look at lithium diisopropylamide. Why, so exciting to see powerful reactions and powerful reagents that really do stuff. Way back in the chapter on alkynes, we introduced you to a new base, and they just kind of blew through by it so fast, and they made it hard to remember. It's like, is that the same as sodium in liquid ammonia, or what's NH2? This base is called sodium amide. It's like an NH2 minus. And this new base that we're teaching you about, this new base that we call LDA, lithium diisopropylamide, let's go ahead and draw that out. What is the difference in the similarity? Let's compare and contrast these two bases. So this is the new base for this chapter, and you're going to be using it in the next chapter heavily too. You already learned about a very similar base, sodium amide. So what's different here? Well, there's some pretty substantial differences related to lithium versus sodium. Let's just set those aside right now. I want to focus on the obvious difference. And the obvious difference is that these isopropyl groups are sterically encumbered. They have just the right amount of sterics. They're really bulky, but not so bulky that you can't use the base effectively, but have just, and somebody spent a lot of time trying one isopropyl, one ethyl, two ethyls, one isooctyl. They tried everything. And this is the one that has just the right combination of size and basicity to be super powerful. And the basicity of this is about the same as the basicity of sodium amide, but this is very sterically hindered. So let me just write that here, sterically hindered. No problem using it to deprotonate next to carbonyls. It's not that hindered where you can't reach in and pull off a proton. But that's the main difference. And if you want to think about the reactivity of these, it's kind of similar to what you might expect a free amide anion, the kind of reactivity that you see. It's not to say that these act through free amide anions. It's the lone pair on these species that's pulling off the proton. We don't need to worry about the details of that arrow pushing. We can use the symbol B unless I tell you to specifically use that species in there. But this is just a crazily basic species, way more basic than hydroxide anion. How would I gauge the basicity of this versus hydroxide? Well, I would draw the conjugate acid from these bases. The conjugate acid would be diisopropylamine. The conjugate acid here would be ammonia. The conjugate acid for an alcohol or for hydroxide would look like that. It would have no H bond there. And so the pK of these two amine species to pull off those protons, Those it depends on the substituents, the types of alkyl groups that are attached. But you're going to find that the pKs are somewhere in this range of 38 to 40. And when you get to something that's that not acidic, so unacidic, does it really matter whether it's 38 or 39 or 40? You are so far away from the pK of an alcohol OH, which is a pK of 16. Does it really matter whether it's 24 orders of magnitude or 23 orders of magnitude? Not really. I mean, these are so, once you deprotonate these, you have such an aggressive base over here. It's really hard to get the proton off, but once you get the proton off, these are crazy hot bases, great for pulling protons from next to carbonyl groups. And that's really what we're doing in this chapter. Wow. Now let's talk about the effect of that steric hindrance. Again, I told you somebody spent a lot of time trying 2 isopropyls, 1 ethyl group. There's no way you could predict what are the right alkyl groups to have on an amide base when you're deprotonating next to carbonyls. Let me explain why that sterically hindered lithium diisopropylamide, LDA, is a super important base. Now, I'm going to show you a very special set of conditions that you have to memorize when you use LDA. And I want you to write this down. I don't ever want you to just write LDA. I want you to write LDA in THF at minus 78 degrees. You have to write those 3 things down every time. And you might think, I'm just I don't have time to write those 3. Yes, you do, because I won't give you points if you don't write those things down. Now, if you use these very special conditions to deprotonate next to a carbonyl, LDA is exquisitely regioselective. So when you have a carbonyl compound, a ketone that is not symmetrical on both sides, one side has 1 H and a methyl group, the other side has 2 H's, that extra methyl group creates enough steric hindrance with the LDA that the LDA will selectively deprotonate on the less hindered side. Selectively. It's amazing how selective it is. I mean, there's the selectivity. So what you end up getting here in this case is the less substituted of the 2 possible enolates. Here's the enolate you get. And don't worry about whether it's R or S stereochem. There is a stereocenter. Don't worry about that. I just want to focus on the substitution pattern. And what you don't get out of this is the deprotonation on the other side, which would lead to a more substituted enolate. So, I mean, LDA is so selective. And it's so powerful, you get 100% yield, and it's so selective, the ratio of these 2 possible deprotonation products is 100 to 0. So picky and so choosy. Wow. Why is that extraordinary? Because from the very start of organic chemistry, what you've learned is that if you have 2 alkenes, if all else is equal, like they have the same carbon backbone, what you've learned in the field of organic chemistry is that less substituted alkenes are less stable, and that's true. Whereas more substituted isomers, if all else is equal, are more stable. We have catalysts, I'm not going to talk about those, but we have catalysts that will isomerize alkenes, and they will isomerize this less substituted alkene to the more stable substituted alkene. That's the thermodynamics favors that, and it's exactly the same for enolates. More substituted enolates are more stable. When you deprotonate with LDA, you get the less stable product in high yield. You get the less stable enolate. In this case, LDA, less stable enolates form faster when it's just a matter of regiochemistry. The less stable of the 2 possible enolates forms faster. And this is the opposite of carbocation formation. Way back in some earlier part of the course, we taught you that more stable carbocations form faster. And you probably thought that that meant more stable things always form more quickly. That's only true about half the time. The other half the time, it's the less stable thing. So it's going to take you a long time to get around that kind of thinking that more stable things form faster. That's not true. In this case, the less stable thing forms faster. We call the thing that forms faster the kinetic product. So whenever a product forms faster, as long as it's formed irreversibly, we refer to that as the kinetic product. So the thing that forms faster here is the kinetic product. And sometimes the kinetic product is more stable, but not always. In this case, the product that forms more slowly happens to be more stable. And in this particular case, the kinetic product and the thermodynamic product are two different things. So sometimes we refer to this as the thermodynamic enolate. It's the more substituted enolate. More substituted alkenes are more stable. More substituted enolates are more stable. So LDA, that hindrance, the steric hindrance of those isopropyl groups, makes it possible for it to be very picky and choosy about picking a proton off of the less hindered side. This is only true when the H's on both sides have the same pKa, essentially. It's like if you've got two carbonyls, if you have another carbonyl here, then it's not, they don't have the same acidity. You know, the proton that's between two carbonyls is going to be the one that gets deprotonated. And sterics isn't going to help you fix that problem. But when you have two, when the CHs on both sides both have about the same acidity, and it's just a matter of more alkyl groups on one side versus the other, the LDA goes after the less substituted side. So more substituted enolate, in this case, is going to be the thermodynamic product. So we'll call these the thermodynamic enolate and the kinetic enolate. So in this case, the product is an enolate, the kinetic enolate and the thermodynamic enolate. Since we're specifically talking about enolate chemistry. Okay, when we come back on Friday, we're going to start using these enolates. We're going to, over and over again, it's going to be this process of deprotonate next to a carbonyl and then use that enolate to attack things. And I'll show you a few extra reactions for things that are going on alpha to the carbonyl group. But just get used to this idea of forming powerful nucleophiles by deprotonating next to carbonyl groups. All right, go study a bunch of reactions, go practice reactions, go work problems in the textbook and in the Sapling online homework system, and try to stay sane and stay healthy and stay safe. I'll see you guys on Friday.